right?
Who?
Darwin Chang.
Oh, Darwin Chen is a physicist.
Yeah, he's a physicist, yeah.
But he passed away.
Yeah, he passed away. Yeah, that I know, because I knew him quite well. I was in Chicago, so he passed away. Very sad, very, very dynamic, upcoming and good scientist.
Yeah, very good scientist. I know him when I was graduate student. So you have an overlap with Dr. Zhang, Professor Zhang.
Yeah. In fact, I was in University of Illinois at Chicago. And
I see.
Where then he was in, this Evanston, Northwestern University.
Yeah. Yes. It's very sad that you're a good scientist. Yeah.
And I did finally my PhD from Rochester, University of Rochester, where Hong, our Hong was, this Hong Mandel parameter. Hong was our senior, 2 years senior to us.
Okay.
Working with Mandel.
So now in India, also still in lockdown situation.
Yeah, it has come down. It has come down significantly, but people have started behaving like normal. So we are scared one more wave will come.
And did you get the vaccine already?
Yes, one round.
That's one. Okay.
Yeah.
Good.
It is that AstraZeneca, which is produced as Covishield in India.
Okay.
How about you?
Taiwan are also in a lockdown, but myself, I haven't got the vaccine yet. I'm still in a queue, in a long queue to get the vaccine. Yeah.
But I guess Taiwan that way is not is okay, right? I mean, it's not a big problem yet.
Relative okay. But in the past months, we started to experience, an increase of the number of infection. So we have the lockdown already for 1 month.
Yeah. Very, very unpredictable. It cools down, then suddenly again it flares up.
Yeah. So now we already have 9 participants here.
Yeah, I will just wait for 2-3 more minutes because this is the time.
Okay, no problem. Okay, 2 more minutes.
Then we'll slowly start. Yeah. Have you been to India?
Yes, I've been to India once. I remember in 2018, but me and my several colleagues, we went to this Dharamsala to see Dalai Lama. We have a meeting on this quantum physicist with Buddhism.
Okay.
It is my first trip to India.
Was by any chance Zeilinger there? Because Zeilinger usually goes there. Anton Zeilinger.
Pardon me? So who?
Zeilinger from Vienna.
From Vienna. Yeah. Zeilinger from Vienna.
Zeilinger usually goes to Dharamsala.
Yeah. He is a friend to Dalai Lama. Yes.
Yeah. So Professor Chen, let me introduce Professor Chiranjeev Mitra, our colleague here. Who will be taking
Professor Mitra, yes, he will be my the chair of this session.
Chiranjeev was a product of TIFR. Then went to Cambridge, then University College London, then back here.
Okay.
He's actually deeply involved in the entanglement and its manifestation in physical systems, spin chain.
Spin chain. Okay.
Spin chain.
Yeah.
So the first work from India, and I guess the world about the entanglement's role in heat capacity and susceptibility was done by him from here.
Okay.
Prashant, I just realized that you have kept Vlatko-Vedra's talk on 2nd July, and I am traveling on 2nd July.
Let me all try to arrange it, rearrange it.
Okay.
Yeah, I'll do that.
Yeah. I will give you Praveen's schedule. Okay. I think so this will go on till 14th July, right?
14th, and there are two special sessions, 15th and 16th. One on Berry's work, one on random matrix and manifold theory.
Okay.
Yeah. So I think Chiranjeev, you can start because
we can start
joining.
Yeah. So are we on YouTube live?
Yeah.
Okay. Let's start. Okay, so so it's a special pleasure to have Professor Yueh-Nan Chen from National Cheng Kung University, Taiwan, who's going to be talking about benchmarking quantum state transfer in the cloud. And just to give a bit of a introduction to Professor.
A little louder, Chiranjeev, little louder.
Okay, yeah. Just to give a little bit of introduction to Professor Cheng is that he was a holder of DART scholarship, and he was at the theoretical physics department in University of Hamburg from 2000 to 2001, and he was a postdoctoral research fellow in the Department of Electrophysics, National Chiao Tung University in Taiwan from 2002 to 4, and he was adjunct assistant professor in the same place from 2003 to in the year 2003, and from 2004 to 6 he was postdoctoral research scholar. Then from 2006 onwards, he joined National Cheng Kung University as an assistant professor in the Department of Physics, and he was an assistant professor till 2010. And then he was promoted in 2010, and 2010 to 14, he was associate professor, and he has been a full professor since 2014. Among many accolades, Professor Cheng is also in the editorial board of scientific reports. So I would just hand over the floor to Professor Cheng without further ado. Professor Cheng.
Okay, thank you for the introduction. So first of all, I would like to thank the organizer for the chance for me to give a talk here. So right now I'm going to share my screen, okay? So can you see the screen?
Yeah, we can see it.
Okay, so today I'm going to talk about this benchmarking quantum state transfer in the cloud. So in the cloud means that I will show you later. Then we use this quantum computer remotely. For example, IBM Q or QTech. We're going to use this quantum computer in the cloud to try to demonstrate some experimental result. So I'm from Taiwan, National Cheng Kung University. Right now, we also have a new center here called this Center for Quantum Frontiers of Research and Technology. So in short, we call our center as QFORT. So please, before my talk, please allow me to briefly introduce my city. So you see from the left figure, you see that Taiwan is next to China. So if you enlarge, so here's a map of Taiwan. So you see the capital is Taipei in the north of Taiwan. And I'm in the southern part of Taiwan. We call it Tainan. And Tainan is actually the first city of Taiwan. I think it's from 400 years ago. And at that time, I think the Dutch, the people from Netherlands first occupy a small area here in our city. And they have a castle here. We call this Amping Fort. So our center is some kind of, take this fort name, and we have a Q fort in our university. So as you all know that roughly 2 years ago, and the company Google, they have demonstrated the so-called quantum supremacy using a programmable superconducting processor. They have a 53 and 54 qubit. They can demonstrate an algorithm that is can be done within, let's say, two minutes or something, but in a classical supercomputer, you need to say 10,000 years to finish this job. So this is the very first quantum supremacy. And also last year in China, Professor Jianwei Pan in the group, they also demonstrate this quantum computational advantage using photons. So this is a second quantum supremacy people have seen in the quantum computation. And in addition to this quantum computation, we also have this quantum satellite also from this Professor Jianwei Pan's group. They sent a satellite in 2016, and its name is called MORS satellite. So now people can already demonstrate this ground to satellite quantum teleportation. So this is for quantum communication. So in the past few years, we've already seen a lot of progress on this computation and quantum communication. Okay. So, and in my talk, I will start from a very simple introduction from this cavity QED system. So if we talk about this cavity QED, we can recall that the Nobel Prize in Physics 2012 was given to Harosh and Yueh-Nan for their groundbreaking experimental method that enable measuring and manipulation of individual quantum systems. Okay, so this cavity QED system can be seen, can be viewed from this figure. So imagine you have a two-level atom, and you put this two-level atom in a cavity, very good cavity. So now you can write down the coupling between the two-level atom and the cavity photon. So here sigma plus is the creation operator of the two-level atom, and B minus is the annihilation operator of the cavity photon. So you also have a sigma minus, B plus. Then you have a coupling strength between them. Then you have G coupling strength between the two-level atom and the cavity photon. So with this interaction, you can write down the state of the system. Here you see plus 0 means the electron of the two-level atom is in the excited state, no photon. And minus 1 means that you have an electron decay into the ground state, and you could create a cavity photon, 1 here. So with this interaction and the state vector, you just need to put this into the time-dependent Schrodinger equation, and you can work out the coefficient here, f plus t, f minus t here. So under a perfect situation, you just see there's a f plus t, f minus t, just a sinusoid function, right? So here is the experimental result. I quoted this from this review paper by Harosh. So you see, and the result is that initially you put the electron in the excited state, then you let this two-level atom passing through this cavity photon. Then this means you turn on the interaction as a function of time. So you see, if the interaction is very small, so you see you measure the probability of the electron still in the excited state as a function of time. So you see if the passing time of this two-level atom is very short, so you see that the probability of the excited state is still very high, but when you let the time of the two-level atom in the cavity time increase, you see at certain time, say the time argument is equal to pi over 2, you see that you measure the probability of the two-level atom at some point of time is, you see here is 0.5, the probability is 0.5. So for this particular time, we said that we already create a state of the superposition of this plus and minus state, right? So the quantum state in the superposition state in this cavity QED system. Okay, so we see this beautiful oscillation here. Of course, the cavity is never ideal. You have some loss, gamma, atom decay, and the cavity loss. You see this amplitude will gradually decay. Okay, but you can still see this beautiful oscillation. This quantum Rabi oscillation. Okay, so now because this the growth technology of nanofabrication, now people can also demonstrate this Rabi oscillation in this double dot device. Already 20 years ago, people can do this. So now imagine you have a two-dimensional electron gas. This device, then on top of this gate, you try to fabricate this metal gate. Then you apply the negative voltage on this metal gate. So you see this top view here, you can use in this gate to create the two region for this two-dimensional electron gas. If this left and right region is small enough, then you can imagine from the basic principle of quantum mechanics, you can see this the left and right region, the energy level is quantized, right? So it's like an artificial atom, then we call this a quantum dot. Now we have a left dot and right dot, and the energy level is quantized. So for this double dot structure, we can also connect this to a source and drain, left electron reservoir and right electron reservoir. So in principle, now an experimentalist can initially prepare an electron in the left reservoir, then let this single electron tunnel into the left dot, then tunnel into the right dot, then in the end, tunnel into the right electron reservoir, just a single electron, right? And because this barrier is controlled by this the voltage we apply, so in principle, we can make this central barrier width very thin, so that the electron in the, let's say in the left dot, the wave function can penetrate into the right dot. On the other hand, if the electron is on the right dot, then the wave function can also penetrate into the left dot. So under this condition, you write down the interaction of the system. Is the Hamiltonian is written like this. You see here we have the energy spacing of these two levels is energy here. We also have energy penetration. Then we have interaction, the delta mass sigma x operator, right? So now we have this off-diagonal, the coupling in the Hamiltonian, right? So if you look at this Hamiltonian, it's exactly the same to the cavity QED system I have just shown. Then, so now experimentalists can do is that initially they shift this two level very far away. So in this case, there's no coupling here. Then for this case, then you can put one electron into the left dot. Then you very quickly align these two levels. That means you turn on the interaction delta sigma x here. That means you let the system evolve for a certain time, TP here. Then after this evolution, you quickly shift these two levels away. That means you turn off this interaction. Then on the right-hand side, you try to look at whether the electron is in the right dot or not, right? So it's exactly the same, identical to the cavity QED system experiment. So if you have very good sample, the temperature is very low, then you could see this same Rabi oscillation in this experiment, right? So when you see this, you say, okay, I see this at some point of time, the electron is delocalized among these two levels, right? You see, there's a superposition state of this case in your experiment. But if you think this experiment result carefully, you might have a question that is it possible that the electron is never delocalized among this two-level dot? It's just the electron is always a particle. It's just due to some unknown mechanism. For example, it is possible that the electron is never delocalized, never in a superposition. It's always a particle jumping back and forth between these two levels and also give you the same result, okay? Never delocalized, but give you the same oscillation result. If you think this question seriously, it is possible, okay? So I'm going to show you a very interesting example. Then this is I call this this crappy experiment by these toys. We call this a robotic box. So if you go to, this is the toy I borrowed from my kids. And you see this a robotic cockroach, okay? So you put it into the battery and turn on the switch, then its leg can move. So when you buy this toy, you also have the home for this cockroach. So I say this, the white area is the left dot, and this the gray area is the right dot. So every time I always put this cockroach on the white area, then let the cockroach moving around this white area and gray area, right? And then I ask my student to recall the probability the cockroach is still in the white area, okay? So you see, you clearly see, so this is experimental result. So I asked my student to play this, to run this experiment many times. You see this probability, the cockroach is still in the white area. The white area show you this beautiful oscillation, right? Then of course, the cockroach is never delocalized, right? It's a microscopic object, right? It's a jumping back and forth between this white area and the gray area, right? So it's a classical object, never quantum, never delocalized, right? So therefore, when the experimental result, you see this Rabi oscillation cannot guarantee it's really quantum. It's possible due to the classical force signature. So we need a way to distinguish this distinguish between classical and quantum, right? So you think about how to distinguish classical and quantum. So you might immediately have a thought that maybe in the textbook of quantum mechanics, my professor told me that there's a way to distinguish quantum and classical, right? There's a Bayes inequality, right? There's what we have learned in the textbook of quantum mechanics. So when we record this Bayes inequality, right? So we have two assumptions, right, on this Bayes inequality. So the one assumption is locality, another assumption is realism, right? So locality means that you have a two particle. One is on the left-hand side of the universe, the other is on the right-hand side of the universe. So if you perform some measurement on the left-hand side particle, because it's too far away, you can never influence the result on the right-hand side particle, right? Because it's too far, so it's locality. And realism, the easy way is that before you perform some measurement, there's no such thing of superposition. It's already in the 1 or 0, right, before you do the measurement. So under these two assumptions, now let's consider the two particles created in the central universe. One particle sent to the left-hand side, the other particle sent to the right-hand side. So on the left-hand side of the universe, you can perform the capital A or small a measurement on the left-hand side particle. On the right-hand side, you can perform the capital B and B measurement on the right-hand side particle, right? So under these two assumptions, we can assign the measurement outcome of our result, right? So we say that if we measure the spin of the system, then if the spin, we measure the spin up, we assign the result is a positive 1. If it's a spin down, we assign this value as negative 1. Then we can do some simple algebra. Then we let the outcome capital A minus A is and the capital A plus A. The result could be 0 or plus minus 2 or plus minus 2 0, right? Because it's A is the value is either 1 or positive 1 or negative 1. Then we let this algebra a little more complicated. We let this A substrate small a multiplied with B, then substrate A plus A multiplied with small b, right? Then if you do this, just put into the value plus 1 or minus 1, then the value could be either positive 2 or negative 2, right? It's simple algebra. Then if you do the measurement many times, then we take the average value, right? Expectation value. Because it's always 2 or minus 2, right? Then you do many measurements, then perform the average, then the value must be, between 2 and minus 2, right? You take the absolute value, then it's bounded by the value of 2, right? So this is results under the assumption of locality and realism. Then, but if you think go back to the quantum mechanics course, then professor told you that wait a minute, that when we calculate the expectation value, this A, B, this kind of stuff is no longer a value, right? It's an operator. So in a quantum mechanical calculation, so if we sandwich this expectation value, then we need to, the sandwich is a cat and brown, right? So therefore, if you measure this AB operator is the direction of the spin, then a simple quantum calculation give you that this expectation value of AB is the angle of this the spin direction. This is a two spin direction, the minus cosine theta. Theta is the angle between these two measurements. So therefore, if you properly choose your measurement direction, let's say it's x, y, or sigma y minus sigma x, or sigma y minus plus sigma x, then there is a way that under quantum mechanical calculation, this value is greater than 2. So therefore, this Bell's inequality allows you a way to distinguish your quantum and classical situation, right? So actually, starting from 1980s, already people have some experimental result on this violation of Bell's inequality. But of course, there's always a debate on this loophole. Until 2015, there are 3 experiments that claim they close the loophole, at least to some extent, on this Bell's inequality measurement. Okay, so this is a brief introduction of the Bell's inequality. So now, with this Bell's inequality, we can introduce the Legge-Garg inequality, also called the Bell's inequality in time. So now, let's forget about 2 particles. We just focus on a single particle, a single object. But this single object is we assume it's a macroscopic object. So in 1985, Legge and his colleagues and they assume that if we have a single macroscopic object, because it's a macroscopic, basically we have 2 assumptions, right? The first assumption is realism, because it's a macroscopic object. We basically, because I'm close to the macroscopic world, so we can assume that before we measure it, it's already in the value 1 or 0, right? Before we do some measurement. Then for this macroscopic object, because it's macroscopic, so basically we can also assume there's the non-invasive measurement. That is, we can perform measurement without disturbing this system, right? So under these two assumptions, so basically, if you have an observable A and its value is bounded by unity, then under this assumption, then we can write down this inequality for this two-time correlation function, 82, 81, 83, 82, subtract 83, 81, and this is bounded by the value of unity. Right? This is under these two assumptions. But again, and in quantum mechanics, this A operator, A value, this A is an operator, not a single value. So in the quantum mechanics, if you calculate this two-time correlation function, there's a chance to see the violation, right? Okay, so now I guess in 2010, in the first experiment on this violation of the Lagrange inequality is done on the superconducting circuit. It's a micro-sized system. You see here, we have a 1 point violate this inequality. Okay, so of course, a later experiment is also see some more violation of this Lagrange inequality. Okay, so now at that time we also played around with this Lagrange inequality. So we try to write a variation form of Lagrange inequality and put it into this double dot system. So now we have this transport version of the Lagrange inequality. So you see this, our model is here, electron turn into the left dot, then the electron between the left dot can turn into the right dot, and then turn into the right reservoir. So we assume that if on the right-hand side, we have a charge detector, we can perform this non-invasive measurement. Then we put into this result into the variation of the Lagrange inequality. So if you can see the violation, then you are more likely to say, okay, this is a transport problem, it's a double dot system. You see the oscillation is quantum, not the classical force signature, because you see the violation of this Lagrange inequality. Okay, this is a way to distinguish classical and quantum case in this double dot device. So now the third thing I would like to introduce is the quantum steering. Okay, so the concept of steering actually was you can trace back to this 1935. At that time, the Einstein, Podolsky, and Rosen, they have a challenge that there's we call this the EPR paradox. The challenge that they said is quantum mechanics is incomplete. Okay, and now at that time, actually, Schrödinger gave a response. He said that it's not the incompleteness of quantum mechanics. It's a resource. It means that Alice, when she performed a measurement on the left-hand side particle, actually, he can steer Bob state on the right-hand side into an eigenstate of one of these. Okay, so at that time, Schrödinger proposed the word steering, this kind of concept, but at that time he didn't get any mathematical formulation. So until 2007, and people has write down the formula of this steering. So right now in this community, we have this three different forms to basically to describe the quantum non-locality. So the first is represented by figure A. So now Alice Bob, so you trust the measurement device, both on Alice and Bob's device. You trust their device. So it's a white box, right? So you trust their measurement result. So if you want to make sure the two particles on the left-hand side, the Alice and Bob side, you just tell them to perform the quantum state tomography. Then with this result, you can construct the density matrix. Then you put it into the formula, and then you can tell, okay, the state is quantum or not, right? This quantum state tomography. You can tell them if the state is separate or not, right? So this is figure A. But now the figure B is the Bell's inequality. So there's a third person, Charlie. So Charlie does not trust the Alice and Bob's measurement device. So now their device is a black box. But Charlie wishes to know if their particles are entangled or not. So Charlie asks Alice and Bob to perform some measurement and return their result to him. Then Charlie put their result into the Bell's inequality. If he gets the violation, so Charlie has to admit, okay, Alice and Bob, your result, your particles are entangled. So this is the Bell test, the Bell's inequality. So steering is between A and B. So now there's no third person Charlie, just Alice and Bob, okay? So Bob on the right-hand side, he trusts his own measurement device, okay? He trusts himself. So now it's a white box. But Bob himself, he does not trust Alice's device. So on the Alice side is a black box. But Bob on the right-hand side wishes to know if the particle they share is entangled or not, okay? So Bob then asks Alice to perform measurement and return the measurement result to him. Then according to his measurement result, Bob himself performed the quantum state tomography on his device. Then under this spirit, so we can construct with the so-called steering inequality, very similar to the Bell's inequality. So here S is the so-called steering parameter, right? And P is the probability of the Alice measurement outcome. Alice chooses his measurement observable on capital A with outcome A, and this is probability. Then Bob condition on this measurement outcome and perform his trusted measurement. You have a measurement result B, and this is forms an inequality very similar to Bell's inequality. If violation of this inequality, then Bob has to admit that his particle is entangled with Alice's particle, okay? So this is steering inequality, okay? So there's a hierarchy among these three different forms to describe this non-locality. So we can use the Warner state to test this hierarchy relation. Okay, so Warner state is the combination of this single state and identity, right? So we have a V coefficient here before this Bell single state. Okay, 1 minus V before this identity. So if you use the Warner state as a test to show the violation of Bell's inequality, you need this V larger than this 0.65. Okay, so this is the most strict the condition. But if you want to see this EPR steering, you only need this coefficient V larger than 1/2. Okay. Then to demonstrate this non-separability, I mean this the white box result, the phenomena, you only need V larger than 1/3. Okay, so this is a hierarchy. This is a hierarchy of this three forms of non-locality. Okay. Okay, now here comes the puzzle. Here comes the puzzle. Now, on the top row, left-hand side, we have this Bell's inequality, right? For two particles. On the top row, right-hand side, we have Legate's inequality, for a single particle at a different time, right? So the second row, left-hand side, we have two particle EPR steering inequality. Then we can ask a question. The second row, right-hand side, do we have a single particle temporal steering inequality, just like the Legge-Guy inequality to this Bell's inequality? And of course, the answer is yes. So we can borrow the idea from this Legge inequality. Now we just focus on a single particle. So initially on the left-hand side, we have a single particle, single spin. So at time ta, there's a person, Alice, she claims she can perform the non-invasive measurement on this particle. And he get this untrusted result. Then after her measurement, the very same particle is sent into a channel, right? Then a later time, TB, Bob performed his trusted measurement on the same particle, right? Because this mathematical formula is the same, so we can write down the same steering inequality, right? Just like this EPR steering inequality. So we can have a very simple example on this temporal steering inequality. Then initially, let us assume we have prepared a qubit in a mixed state, then time 0, Alice perform. Then we evolve in run. Just in the so with this Alice result at T0 and Bob result at the time T, you can put into the temporal steering inequality.
Hello?
So I'm sorry, somehow I lost the connection. So can you hear me now?
Yeah,
we can hear you.
I'm sorry. I think I lost.
Yeah, we were thinking, is it a problem at our end or your end? So
I didn't aware. Sorry, I lost my connection. So I'm going to share my presentation again. Sorry, I don't know what happened. So can you remind me when did I lose my
36 slide.
in which?
36.
Is it this slide or previous?
Yeah, this one. Yeah, this one.
This one. Okay. Sorry. Okay, let me restart again. Sorry. Okay. So we wish to test this temporal steering inequality, right? So initially we have just a focus on single particle. So and initially we have a spin, and we at the time TA Alice, she claims she can perform the non-invasive measurement, right? Then after her measurement, the very same spin, the qubit is sent into a channel. Then a later time TB, Bob performed his trusted measurement. Okay. Then because this is very similar to the EPR steering, then we can write down the mathematically the same steering inequality, right? Then we can have try to test whether there's a violation of this temporal steering inequality. Then we have this simple example on this single qubit under Rabi oscillation. So initially we prepare a qubit in this mixed state. So at time t0, Alice performed her measurement, and at later time t, Bob performed his trusted measurement. And between these two measurements, the qubit is put into a Rabi oscillation channel. Okay, you have a coupling G and decay gamma. You can see right after the Bob measurement, you can always see a violation. But this is simple to understand because there's no such thing in there's no such thing of this non-invasive measurement here. The Alice measurement always disturb the system, so you always see the violation. So then, what's the big deal of this temporal steering inequality? So we sort of try to connect this to the BB84 quantum cryptography. So in the BB84 quantum cryptography, it's a simple idea is that Alice sent a string of qubit to Bob. So they try to encode some information on the string of qubit, but they wish to know whether there's a third person, say Eve, try to steal the information. So they use the concept of this whenever you measure a quantum system, you always disturb it, right? So they use some qubit to do the test, to do this equality test. If there's some error, the error rate is larger than to some value, then they will know the channel is no longer secure. So if you look at the BB84 protocol, if this error rate is larger than this 14%, then they know this channel is insecure. So then we have, at that time, we have checked that if our steering inequality start not to violate under the incoherent tech, then this when the steering inequality start not to violate, then at this point it's exactly the same to this error rate, to this 14%. That means this BB84 concept can be understood from the angle of the temporal steering. Okay, so the later we have some experimental result demonstrate that the violation of the steering inequality, temporal steering inequality. You see this solid curve is the theoretical prediction of this temporal steering. This dot result is the experimental result by photons demonstrated by a group at Poland. Then we can further quantify this temporal steering, and we use the concept of this temporal steering assemblage. I will explain later. So if we quantify this, we can use this quantification to become a measure of non-Markovianity. So what is a non-Markovian? So is the easy hand-waving way to explain the non-Markovian that imagine you have a two-level system, electron, you put it into the free space, the electron decay into the ground state and emit a photon. The emitted photon never comes back. So you see this monotonic decay. Then just like this the green curve here, then we say, okay, this system undergoes a Markovian environment, right? But somehow if you put this two-level atom in a cavity, so this cavity photon meet this wall and bouncing back and re-excite this two-level atom, then you can see this revival in some physical parameter. Then sometimes we just a simple idea say the revival of something is a physical, the quantity, then this is a non-Markovian. Of course, this is the hand-waving explanation of non-Markovian behavior. So speaking of this, our temporal steering, so we can using this so-called temporal steering weight to do the quantification of the temporal steering. Okay, right now I have no time to explain in detail the concept of temporal steering, but just remember we can quantify how much the steering is. Okay, then using this quantification, then together with this condition of this, we apply a CP-TP map of this stable weight, and we proved that this is the non-increasing function. If you apply a CVTP map to this temporal stable weight, then together with this condition of divisibility, then we can prove that we just integrate this positive slope of this temporal stable weight can give you a quantification, a measure of non-Markov-unity. Okay, so that means that we just integrate the positive slope of the temporal stable weight can give you a quantification of non-Markov-unity. Okay, so here is some simple example. You see here, if we put our two-level atom in a Markovian environment, you see this temporal stable weight give you a monotonic decay. You see, so there's no non-Markovian here. But if you consider the two-level atom is a coherent couple to another qubit, so you consider the left qubit as your system, the right qubit is your environment. Of course, you see some oscillation between this system and the environment, right? But if you just look at the system, then you see, you calculate this temporal stable weight, you see this a revival of this temporal stable weight, then you just integrate the positive bar, you get this non-Markov-unity of the system, okay? So quantify this temporal stable weight can give you the quantification of non-Markov-unity, okay? So later there are some experimental group in mainland China, they use the photon to demonstrate this non-Markov-unity, right? You see this, the solid curve is the theoretical prediction, the dot line, the dot are the experimental results, so which fit the theoretical prediction very well, okay? So now we can also generalize this temporal steering to the so-called spatial temporal steering. Now we have again come back to the two-particle case, but the measurement are performed at a different time. So now you see we have a two particle, the upper particle and the lower particle here. So at earlier time, you perform a measurement on the upper particle. Then after the measurement, you send these two particles into a channel lambda. Then that system evolves for a certain time. Then the later time, you perform a trusted measurement on the lower particle, right? So again, with this idea, you can write down this spatial temporal steering. So with this spatial temporal steering, you can use this to, we sort of prove we can use this spatial temporal steering to test in a network whether, let's say, between A and B, whether there's a non-classical correlation between this network A and point A and point B in a network, okay? So now we can also use this spatial temporal steering to quantify the quantum causality, but due to this time limit, I have no time to explain this. Okay, right now, I am going to tell you that I hope I have convinced you that we can see this quantum steering is a resource. So we can use this resource to do something. So now I'm going to tell you that we can use this resource to benchmark the quantum state transfer in IBM, in a quantum computer in the cloud. Okay, so now the quantum task we wish to do is to do this quantum state transfer. Okay, I'm going to show you later that we have a result on the IBM Q and the quantum device in QTech in Netherlands. So the text of the quantum state transfer is that, so you see on the left figure, initially we have a state, quantum state, particle A, we have a rho A state. So then we have a state, the particle B. So after the evolution, we hope we can transfer the quantum state from particle A two-particle B after some evolution, okay? So this is the picture, the concept of quantum state transfer. But if you look at the concept of this, the spatial temporal steering, so you see, again, we have a two-particle, right? The spatial temporal steering. Then the earlier time we perform some measurement, right? Then after the measurement, we let this two particles send into the channel. Then the later time, we perform the trusted measurement on the particle B. So if you look at these two concepts, so it's very similar. So we sort of prove that if you wish to have a perfect state transfer from A to B, it's identically, it's equally to say we have a perfect spatial temporal steering from A to B. Okay, these two is equivalent. So therefore, if we wish to test whether there's a perfect state transfer, it's equal to test if you have a perfect spatial temporal steering from A to B. So again, as previously, I have shown you that we can quantify this spatial temporal steering. Let's say we call this a steering as a steering robustness. It's a quantifier, okay? But now we also have to pay attention to this the so-called non-signaling issue, because in the spatial case, the two-particle case, there's a assumption that because the two particle is very far away, there's no way to signal classical signaling of A particle to the B particle, right? Because it's very too far away. So in the spatial case, the non-signaling issue is always obeyed. But in the temporal or spatial temporal case, there's a chance to violate the non-signaling issue, right? Because you perform the later time measurement, later time, there's a chance to signal it from Alice to Bob classically, right? So you have to pay attention to this non-signaling issue. So now the idea is that we consider a string of qubits. So we wish to transfer the quantum state from Q1 to Qn, right? So if we want to transfer the state from Q1 to Q2, then we turn on the interaction, the H bar, and say sigma plus, sigma minus between the interaction. Then from Q2 to Q3, we turn on the interaction between 2 and 3. So on and so forth. Then with this interaction, we can transfer the state from Q1 to Q1. Then you can try to transform this interaction to a quantum circuit like this. So you just need to initially you do the prepare state preparation on the Q1, the QP1. Then you turn on the interaction. Here you need to the control R and the C0 operation. Then you can transfer the state from 1 to 2. Then 2 to 3, you again use the same theta operation. Then you can transfer the state to 2 to 3. Then in the end, you transfer the state to this Q1 qubit, then you perform the measurement, right? If the device is perfect, no matter how long you transfer the state, you always see the steering. If you you turn on the interaction at the right time, theta here can be viewed as the parameter time. You choose the proper time, then you can always obtain the maximally steering, okay? No matter how long the qubit string is under the perfect situation, you always obtain the very same maximum value of this steering robustness, okay? But in a real case, you always meet the gate error, also the measurement error, right? So if you test this on the IBM quantum device, you see here's the result. You see on the right-hand side, B and the D are the experimental result we perform on the IBM quantum device, Bablingen. The date is January 2020, you see? And the black curve are the result for the transfer of through 2 qubit. And the blue dot are the result for the string 3 qubit. And the red square are the result for the 4 qubit transfer from 1 to 4, 1, 2, 3, 4. And the green cross are the result for 5 qubit from state qubit 1 to qubit 5. You see the magnitude of the string, spatial temporal string, decrease if you increase the number of qubit. So this is easy to expect it, right? Because you increase number of qubit, you accumulate the error, so the magnitude decrease, right? So on the left-hand side, figure A are the result we performed on the March 2020. You can see you got the similar result compared to figure B, right? From qubit 2, qubit 3 to 4, 5, you see the decrease of the magnitude of this steering, right? But if you pay attention to the non-signaling stuff, you can see that figure D, that the data on the January 2020, you see this huge signaling effect on the data here, right? And after they perform the calibration on the device, we see the data of this, the experimental data of this signaling effect. You see the signaling effect is greatly reduced, right? So you can see, although for the different day you obtain the same magnitude of this steering, but this signaling is dramatically different. And the classical signaling is something we don't want, right? Because the signaling gives you the false signature. If you omit this signaling effect, you will think, okay, we obtain this high state transfer. That means a high steering. But actually, your high state transfer comes from this classically signaling effect. It's not a genuine quantum. So therefore, to guarantee your result is genuine quantum, you need to check the signaling. The signaling should be 0 cross 0. Then you can have more confidence that your result is genuine quantum, not the classical false signature. So therefore, I think that we apply this steering concept to, we can benchmark the quantum text of this state transfer to check whether this is good or not only on the steering magnitude, but also you have to check the non-signaling result. Okay, so therefore we think that we can have a benchmark for this quantum state transfer. So we also compare this benchmark on different device. You see on the first column is this result on the IBM result. You see on the Bablingen March 2020, from 2 string qubit to 3 string qubit, 4 qubit, 5 qubit. So the maximum steering, okay, is 0.21 to 0.20, 0.7, 0.22, right? And the signaling is 0.015. Okay, so signaling is not much, right? But if you perform the same steering on the, let's say, on the QTech device, Starmon 5, then we perform this test on May 2020. Because it's a geometry, so on this QTech device, we only have a result for 2 qubit and 3 qubit. You see the steering magnitude is, compared to the IBM device, is lower than this, the magnitude is lower than this result in IBM Q. Also, the signaling is larger than the result in IBM Q. So therefore, in some sense, I would say, if you compare these two devices, the performance of this IBM Q is better than that in the QTech. So on the QTech, you also have this 2-spin qubit. So because 2-spin, we can only test this, the transfer from spin 0 to spin 1. Then you see this spatial strain is very low, just 0.1, and it's almost dominated by this classical signaling effect. So for this, the 2-spin device, so the result is not very good. So I think with this table, I hope I can convince you that with this, the spatial temporal stream, we can give a good benchmark to this quantum state transfer, this quantum task. Okay. Okay, so here is the summary of the talk. So I have introduced you this the EPR steering, and also I also tell you we can have this temporal quantum steering, and we can quantify this, and we have with this quantification we can measure this non-Markovity. Then use this spatial temporal steering, we can benchmark the quantum state transfer in the quantum device, in IBM Q and the QTech. So before the end of my talk, I would like to thank to my collaborator, Dr. Neil Lambert and Frank Nori and Ricken and Professor Adam Minowitz in Poland, and some of my colleagues in Thailand, Professor Hongbin Chen, Dr. Yueh-Nan Chen, he is now in Berlin, and my postdoc Huang Yugu, and my PhD student Ida Huang. So this is my talk today. So thank you very much for your attention.
Thank you very much. There are a few questions. So
okay.
Maybe people who have asked questions who here, maybe, let's see. Abhishek Bhardwaj, why don't you ask the question directly to him? Unmute yourself and ask the question.
Okay, I see the question in the
chat box. You can see, but if they want to ask you directly, they are welcome to ask you directly.
Okay, so please resolve the problem, sir. I don't quite understand what is the problem. Resolve the problem, sir. Sorry. So we need to 1 electron at a time to enter the cavity. How do we manipulate it? So I think in the transport, the double dot case, you need experimentalists now can, using this the Coulomb bracket, they already can really precisely control. So every time only 1 electron is put into the dot. So I think this experimental is they already have such a technique. So every time we can put 1 electron into the cavity using the concept of the Coulomb bracket, right? If you want to have a second electron into the cavity, the dot, the energy cost will be too high. So it's not possible to have the second electron into the dot. So this is concept of electron. The Coulomb bracket. So with this concept of Coulomb bracket, you can make sure every time you only have 1 electron into the dot. So the third question is, how is signaling related to the fidelity of the quantum state transfer? So this is a very good question that I didn't mention that we have proved that the signaling is a lower bound of the spatial temporal steering, right? So that means if the spatial temporal steering is equal to the signaling, the magnitude of the signaling, classical signaling, then we can say the steering is contributed by the signaling effect, not contributed by the quantum. Okay, so that is from the relation that the signaling effect. We prove that in our work is a lower bound for this the spatial temporal steering. Okay, so with this lower bound, this is the signaling is related to the fidelity of quantum state transfer. So the first question is that increase in transfer routes is decreasing the value of signaling. What can we interpret it from this? Okay, let me come back to the result. So the question is that the increase of the qubit string, you decrease the signaling, classical signaling effect. Okay, this is a good question. So probably it's due to that in this, because the signaling is the classical stuff, right? So maybe when you do the transfer things, there is some classical error that can destroy the classical signal. That is, I think the thought came into my mind, but I'm not quite sure. We need to do more analysis on it to check whether this is due to the classical error that decrease the magnitude of this classical signaling effect. So that's my answer for this. Okay. Okay. So this.
There is one question at the top. Abhishek Bhardwaj had asked, in TDEG, do we need one electron at a time to enter the cavity?
Sorry, can you repeat your question again?
See the question asked at the top at 9:18 a.m. by Abhishek Bhardwaj. Maybe you were logged out for some time, that's why you lost it. Maybe what I will do is, I will copy it and paste it here so you can see.
Sorry, your voice is very low. Can you?
Sorry. There is a question at the top in the chat box. Can you see? Asked by Abhishek Bhardwaj. He has asked it again.
It's a question.
Yeah.
In 2DEG, do we need one electron at a time to enter the cavity? Yes, we need one electron at a time. We need in the 2DEG, we need one electron at a time to enter the cavity. So we consider as one electron at a time. Yes.
Okay, I don't see any other question in the chat box. In case the audience.
Okay, I have a question.
Okay, Prashant.
Yeah. Can you go back to the slide where you first time introduced non-Markovianity?
Non-Markovianity. Okay, I go back to the slide. Yes. Here.
Yeah, here the plot is time versus the degree of entanglement, right?
Yes.
And in the green line, it is showing that the degree of entanglement is decreasing exponentially. So this is intuitive, or we can understand. But in case of non-Markovianity, I mean, there is a resurgence of the quantum properties. And this is kind of counterintuitive. Like, what can cause this resurgence?
You mean that what counterintuition? Can you say again your question?
I mean, in non-Markovian systems, we can see that with time, after a certain time, the degree of entanglement is like rising again, then falling down again.
You mean the red curve, the rise?
Yeah, the red curve. Yeah, the red curve.
Okay. As I explained, there's a simple example that if you consider, you see this the two qubit, there's a system and ancilla. The ancilla is in its environment. If you, for example, if you have a coherent coupling between this system and this ancilla, right? So you have coupling G here, right? So G coupling, the inverse of G give you the time of the revival of your entanglement, right?
Okay. Yeah.
Okay. So this is the time related to this coupling G, right? Do I answer your question?
Yeah.
Okay.
So there is a question from Sohan. So can you see the last question, Professor? In the spatial.
Last question, okay. Sorry.
Chiranjeev, I have a question.
Okay.
Yeah.
No, I see. I already see. Sorry. In the spatial temporal steering, how does major second particle after it has emerged from cavity change its state? Also, does the state of the first particle? So in reality, for example, I will use the example to answer this question. So in the IBM Q system, okay, IBM Q, the latest result I show you. So we can use the prepare and measure scenario, okay? So basically, so at time 0, you can prepare your state and then somehow represent at least perform the measurement at time t0. Then after you do the preparation, you let the system evolve, right? You let the system evolve. You turn on the interaction. You let the system evolve, right? For example, you prepare your IBM, the state in the IBM Q system in qubit Q1. Then you turn on the interaction, right? That is system evolve. That is, in some sense, we let it put it into the channel, right? Then evolve for some time. Then the IBM Q system, we can perform the measurement and on any qubit we want, right? So then if we perform the measurement on the different qubit, then we do this, from the concept of spatial temporal steering, then we are doing this, the trusted measurement on both particle. Okay.
Okay, Prashant, you can ask your question.
Yeah, my question is related to causality.
Causality, okay.
When you are looking at this temporal correlation like Leggett God, so I would believe the causality has to be respected or it is already inbuilt.
Yeah, causality. So it depends on what kind of causality you are asking, right?
Mainly, like in special relativity, like the speed of light in that context, that
okay.
you have this space-like domain, then, this time-like, space-like, in that sense, that physical information should not travel faster than light.
Okay, so this Vegas inequality is a trivial. It's always in before and after on the same qubit, right? So it's always the normal causality. Okay?
Yes.
Normal causality. Okay.
Oh.
Okay, there are no further questions. So let us thank Professor once again. Okay, we can.
Right. Well, thank you very much. Thank you for your attention, invitation.